Hi everyone, we are from Session 8 Group 2. The experiment of our ENT assignment is about the factor affecting the induced currents, and our group member had Nyo Chicha, Lai Yongxiang, So Jin-yong, and Teo Jian-Basir. Our objective for the experiment is to investigate the relationship between the number of turns of wire and the type of conducting material to the induced currents.
Next, I will present the theory of this experiment. The theory of this experiment is explained by Faraday's law of electromagnetic induction, which stated the changing magnetic field within a closed loop of wire induces an electromotive force and electric current in the loop. Firstly, in order to produce induced current, a changing magnetic field is necessary. This change can occur either through the motion of a magnet or the movement of a conductor through a magnetic field. Next, the magnetic field passing through a conductor will create a magnetic flux. When there is a change in the magnetic flux, it will produce an induced electromotive force in the conductor. It can express as EMF equal to dphi over dt. Then the induced EMF drives the flow of an electric current in the conductor. We can express it as I equal to EMF over R. According to the Lenz's law, the induced current always flows in a direction that opposes the change in the magnetic flux that produces it. Lastly, the theory of the induced current has some practical applications such as generators, transformers, and electric motors. These devices utilize the principles of electromagnetic induction to generate electric energy.
The apparatus we need for the experiments are copper wire, iron wire, and the multimeter, toilet paper roll, and the magnets. Next, the procedure. First, we set out the apparatus, we set out the experiment as the figure shown here, and then we coil the copper wire to 19 turns to the toilet paper rolls. Then we fix the magnet on the top edge of the toilet paper roll and then let the magnet free fall to the ground. By doing so, we can make sure the acceleration of our magnet is constant since it free fall from the same positions. After that, we record and we observe and record the reading from the multimeter. Then we repeat step 1 to step 4 with 30 turns and 60 turns. After that, we repeat step 1 to step 5 with our iron wire. Because the variable of our experiments are number of turns of wire and the type of conducting material. Next, I'm going to show you how we can carry out the experiments. Here is the result of our experiments. We carry out the experiments 3 times for each number of turns in order to get a more accurate value.
Okay, next we'll move on to discussion of our experiment. Our experiment showed that as we increase the number of turns in the coil, the induced current also increases. This means that the more the turns in the coil lead to a stronger induced current. We can explain this using Faraday's law of electromagnetic induction. With more turns in the coil, it allows more magnetic field lines to pass through it. So when the magnetic field changes, there is a bigger overall change in the magnetic field passing through the coil. This change creates a stronger electric force which results in a stronger induced current. Similarly, we can observe that the relationship between the material used for the coil and induced current. Different coil materials can exhibit varying levels of electrical conductivity, which influences the induced current. Materials with higher electrical conductivity, such as copper, tend to produce a larger induced current compared to materials with lower conductivity. This is because highly conductive materials allow for easier movement of charges, resulting in a stronger induced current.
In conclusion, we have achieved our objective, and the result of our experiment also matches what we stated in the theory part. Throughout this experiment, we have learned that the induced current in a solenoid is directly proportional to the number of turns of wire, and we also learned that the different types of conducting material will affect the induced current as well.
Okay, that's all from our group. Thank you for watching our video.